Hello everyone and welcome back. My name is Mr. Cobalt, and in this video I'm going to be going over how to write nuclear equations for beta decay, positron emission, and electron capture. And I'm also going to do an example of where you do a decay series and you figure out what the final isotope is. And so let's get started on the first one. So in order to do these sorts of problems, you have to know what kind of decay you're working with. So you need to know what alpha decay is. You need to know what beta decay is. You need to know what an alpha particle, a beta particle, a positron, things like that. So if you know what those particles are and you know what's happening during the decay, then writing the equations is actually pretty simple. And also you need to one of the things that also helps is if you know what the particles are and you know the symbol for the particle, then balancing the numbers on both sides of the equation will help you identify what the missing piece is and what the identity of the element that's left over is. So let's go ahead and get started. So beta decay. So beta decay is where you are emitting an electron, and the reason you emit an electron from the atom is because you have a neutron, you have a proton that is emitted, you have a proton that is giving off an electron, and then you get a neutron left over. So a proton breaks down into an electron and a neutron. The other way around. So a neutron breaks down into a proton and an electron. And the way to remember that is the neutron starts off as neutral, so it has zero charge. And then when the electron is emitted, you've got a negative charge that's produced. And then what's left over is a positive charge. And that positive charge is the nucleus. The proton. So if you think of it backwards, well, if you take the negative electron and the positive proton and put them together, those cancel each other and become neutral, and therefore you have the neutron. So that's another way to kind of remember how these are related to each other. So for the beta decay, you have a neutron that breaks down into an electron and a proton, and the electron leaves the nucleus, and you're left with a proton in the place of a neutron that used to be there. Okay, so how do we write this out? So we have BK 249. So you're going to start with the symbol BK. 249 is the mass number. That's going to be on top, 249. And then you look up the atomic number. That's going to be 97. So 97 is on the bottom. And so this is going to decay into some X, some element we don't know, plus an electron. And so the symbol for an electron is going to be 0 for the mass. So we're assuming that the mass number is 0 because they're so small. And then on the bottom, we have a -1 for the charge. And so that's going to be important later when we're balancing the equation. So here we're balancing the numbers. The top and bottom numbers should balance with the top and bottom numbers on both sides. So we have 249 here. We have 0. 0 plus what gives us 249? It's going to be 249. So we stay here at 249 for the mass number. And then we have -1 here. So -1 and what gives us 97? Well, if you break down a neutron into an electron and a proton, well, the mass number goes up by 1. So that's going to be a 98. So 98 minus 1 gives us 97. So what is this element? Well, we got to look up what 98 is. And 98 is CF, californium. So we're going to replace this with CF. Okay. So we went from berkelium to californium, and Berkeley is in California. Okay, so that's the first one. What about second one? We have a positron emission in oxygen 15, O15? Well, okay, so what is a positron? A positron is basically a positive electron. So you're emitting a positive electron, and guess what? How do you get a positive electron? Well, if you're losing a positive charge, then what you end up with is a neutral atom. So in this case, you have a proton, a positive proton, that is breaking apart into a neutron and a positron. So the positron is emitted, and so you're left with a neutral neutron. So here we're gonna start with oxygen 15. This is the mass number. The oxygen, the atomic number is 8. Let me double check that. Yes, 8. And so what we're going to do is, okay, so we write out the positron. Well, it's just a positive electron. So in this case, we're going to have the symbol E. It's going to have 0 mass number, and this time it's a +1 on the bottom. And so again, we're going to have some element X. We'll figure out what X is in a moment, but the numbers on both sides should balance. So 0 plus blank gives us 15. Well, that's going to be 15. And then +1, 1 plus whatever's here gives us 8. Well, that's going to have to be 7. So what is the atomic number 7? Well, we look that up and we get nitrogen. So the mystery element is nitrogen. So this is the nuclear equation for the positron emission in oxygen 15. What about electron capture? So in this case, we have an electron being captured into the nucleus. So you have a negative electron being captured. That's going to combine with a proton, and you're going to get a neutron in place. So again, we start with we're iodine. This is the mass number. That's going to be 111. And the atomic number for iodine is going to be 53. 53. So in this case, the electron is being captured, so that is a reactant. So it's going to be on the reactant side. So we're going to add an electron. So 0, -1. So our symbol for the electron. And what is that going to form? Well, we're going to have X, whatever that element is. 111 plus 0 still gives us 111. 53 minus 1 gives us 52. So now we look up what 52 is. And 52 is Te, tellurium. So X here becomes Te. So that is the nuclear reaction for the electron capture in iodine 111. Okay, great. So far so good. And last one is, what about this nuclear decay sequence of uranium-235? So we're starting with uranium-235, and we're told it goes through an alpha decay first, and then whatever's left over, the daughter isotope, is going to go through a beta decay, and then that daughter isotope is going to go through another alpha decay, and then what are we left with? So let's write that out. So we're going to start with uranium-235. So 235. Okay, so let me write that as a symbol. So that way I can save some room. Okay, so we have U. So 235. What is the atomic number is 92. So that's going to be 92 on the bottom here. So we got our isotope, we got our parent isotope here. It's going to go over alpha decay. Remember, alpha decay, an alpha particle is just a helium atom, helium with a mass number of 4, atomic number of 2. So it's going to lose that particle. So uranium is going to break down into helium, right? So it's going to lose a helium atom, basically. So 4, 2. And so the daughter isotope is going to be what? Well, we got to balance the numbers. So 4 plus what gives us 235? That's going to be 231. 2 plus what gives us 92? That's going to be 90. So if we look up 90 in the periodic table, that's going to be thorium, TH. So that's going to be TH. Okay. So now that's our first step. So we got the alpha decay. Now we have our thorium. So that's going to have to undergo. So we have TH 231, 90. So now the next step in the series is a beta decay. And as we said before, beta decay is where you lose an electron. So that's where a neutron is going to break apart into an electron, and then the proton is going to be left in the nucleus. So we're going to have plus, we're going to have a negative electron, like that. So there's our symbol for the electron particle. That's being lost here. And then again, we have to figure out what our X symbol is here. So 0 plus what gives us 231? Well, that's going to be 231. And then negative 1 plus what gives us 90? Well, that's going to be 91. Okay, so we look up the atomic number for 91, and we get PA. So this is PA. I forget the name of this one. So now we've done our beta decay, and now we just need one more alpha decay. So we're going to take PA, and so PA 230, 231, 91 is going to undergo an alpha decay, so it's going to lose another helium nucleus. So another helium nucleus. So we're going to have an X plus, and then helium. So 4 and 2. And so again, we just need to balance the numbers. 4 plus what gives us 231? That's going to be 228. And then, 227, sorry. And 2 plus what gives us 91? That's going to be 89. And then all we have to do is look up 89. And 89 on the periodic table is actinium, AC. So this becomes AC. So there's our alpha decay. So this is the decay series, or the first 3 steps in the decay series for U-235. If it undergoes an alpha decay followed by beta decay followed by another alpha decay. So I hope this was helpful in trying to figure out and help write your nuclear reaction equations. If you like this video, please like, share, subscribe, hit the notification bell, and write a comment in the comment section. Thanks for joining me, and I'll see you next time.